Schlaefer, which is entitled Feasibility of Basic Visual Navigation for Small Robotic Sailboats.
Well, good morning everybody. First I have to solve another vision problem so that you see some. Just out. Oh, you see some. Whatever. And it's dark. Okay, I hope the resolution works out, and I welcome everybody. Good morning. This is going to be a crowd presentation. That is, you help me to finish the presentation, which I have not done because, initially that was work by Tobias Neumann, who is one of my students. He was with our teams last year, and then he decided to do a bachelor thesis on exactly that topic down here, feasibility of basic visual navigation for small robotic sailboats. Then decided to finish his thesis, and then he decided to spend a year in South America. There he is now, and he didn't prefer Cardiff over South America. For what reason? I can't tell you. The issues, and Roland already motivated that a little bit. We have on our small boats pretty much everything we want to have. We have a position given by the GPS. We have accelerometer, compass, and gyroscope, providing us some sense of orientation. But we also have something else. We have a lot of noise, and we do have latencies, particularly in the GPS readings. And if you have a small boat like that is very agile, then this can be a bit of an issue. So the idea was to consider whether visual navigation, which is essentially well established, you can't see that down there, right? Oh. I could jump up, but I don't know if that helps. Anyway, so the idea was that we wanted to know whether it would help us at all to use visual navigation. And the issue is really that the images go all over the place. The boats are really, really agile. They move a lot. So what we did is we wanted to consider whether our small boats can, in a scenario where we have many boats, that is racing, take any advantage of having these sensors. And essentially what we did there is we took our small boats and we looked for a really small camera, and the really small camera we found was a gun cam. And you see here, this is a boat, this is 50 centimeters, this is a gun cam, and the gun cam is approximately, I don't know, 20 grams or less. And the cam includes a battery. And you see here, this is a cam mounted to our boat. It got wet, yes, it survived still. We don't know why it's not waterproof. And this is a resolution, 30 frames per second. Well, pretty much. You get video data for approximately 1 hour. And of course, we did some calibration initially to just understand how the images we take relate to our boat. And this was all done with OpenCV. What we can't do though is we can't process the video data on board. Like, we don't really have a big computer to do that on the boat, and I'm going to talk about that a little later. So for now, what we did is we did this kind of recording to the SD card, and also wanted to synchronize the data to our onboard computer. So we needed to have some signal here. We bought a little LED, put it up there, and now Paul can't see that, but the guys in the first row can. Down here, that is the LED, switching on and off. So this was kind of our synchronization method for this purpose. And then we actually had some sequence of light signals going on and off, and actually the blue one is a sequence of signals by our onboard controller. This was a Fibonacci sequence. This is the sequence as we find it in the video data, and we just shifted video data and the log data accordingly so that the two overlap, which also helped us to account for any discrepancies in the real frame rate you have there, so you don't really have it on the same speed sometimes. And then what we wanted to do first is, this is kind of our scenario. Those who've been to Lübeck last year know that very well. We wanted to understand whether we can get first the horizon. And so what we did there, or what we do, is we do a Gaussian on top of what the canny edge detector does anyway, and then we take the canny edge detector, so we have an image like this. Well, I have to learn this. Which gives us all the kind of edges, and the next step was then to take the Huff transform and looking for the longest line in these edges, and that should be the horizon. That's what we thought. Ideally it looks like that. In reality sometimes the horizon is not where we want to have it. And the reason is simply that sometimes you do have pretty long edges down here, and we actually, Tobias did that, build a little GUI to study parameters, and you can play back and forth with the parameters, but it doesn't always work. So what we then figured next is maybe we consider some other properties of the horizon. So this is just illustrating that you can play there. And the properties we assume is that the horizon typically remains relatively stable. So consider 30 frames per second, even if the boat is moving rather quickly, the horizon is not jumping out of the image instantaneously. Then the line is pretty similar in consecutive frames. So if we find a line that is happening all over again, then that is more likely to be the horizon. And finally, in our setup, you've seen that we calibrated the camera and we tried that a little bit. The horizon is typically close to the image center. So if we have a line that is completely far away from the image center, it's less likely to be the horizon unless our boat is moving up and down. But, well, for now, that's what we assume. And then we just produce a set of candidate lines. So we have our Huff transform. The Huff transform gives us all the lines in the image, and the lines are sorted by length initially. And what we do is we now look at all the lines defined by the point in the center where they are kind of going through, and then the slope, and we define some sort of similarity or dissimilarity between two lines, and with this dissimilarity we now sort all the lines that we get. And if we do that, then we can say which is the most similar line to the one that we actually see at the moment. Now, next we consider K consecutive images or video frames, and then we get all the longest lines in each of those frames. And what I tried to motivate before is that we now look for similar lines, like we take all the lines in the current frame, the longest ones, the n longest ones, and we look how many times did I find a very similar line before. And the one that happens to have a lot of similar lines in the k consecutive frames before, we call it the horizon. So essentially what we want to do here is to make use of the property that we believe the horizon is not changing all that much. So here you see what that means in reality. Down here the lines change a lot, go up and down, and the slope is changing, so they are not very similar to each other. And here you have typically a number of candidate lines, and one among those typically is the one that we identify. So the next issue then was horizon is nice, but buoys would be better. So here you already see that we highlighted this buoy, and the other one back here you can't probably see very well. And the same idea, though the way to actually get the image data pre-processed is a little different. So we, in this case, did a thresholding in hue, saturation, value color space, did some morphological closing on the resulting binary image, and then some ellipse fitting, because we think most buoys we use are somewhat ellipsoidal. And the rest of the idea is pretty much the same, looking for stable objects like that over multiple frames. And here you see why that can work. So, well, wrong one. Down here you have also some candidates. You have this big candidate here, and the candidates down here are changing to the next frame, so they are not in the same position anymore, so we can't find them again. And the probability that this is actually a buoy down here is going to be lower than the one for the big red ellipse or ellipse. And the last thing we wanted to understand is whether we can actually get some information about the rotation. And to do that, we implemented optical flow, or we actually computed optical flow, also using the OpenCV, the Lucas Granada method. And the optical flow was actually used on the upper part of the image only because here down below the horizon we have all the waves really close to the boat. So we believe that this is getting a lot of noise and directional information that doesn't help us for rotations. However, what's above the horizon has to stay a little more stable, we suppose. So this is just giving you an idea what the optical flow computes. No much motion here, so you see no real vectors. And here you see that there is a rotation to the right in this case. And, well, for the horizon, we evaluated this with 16 frames and used the 3 longest lines. And actually, Tobias went through the pain to annotate all the different frames from all the scenes. And you're going to see he has a lot of scenes and a lot of frames. But he used this little tool which actually proposed the half lines already. And so we had some sort of ground truths to compare against how many of those horizons do we find. And same for the buoys, he actually annotated all the scenes with the buoys. And for the optical flow, we just compared to the log data as I explained before. So here are the 5 scenes you also find in the proceedings, just illustrating how different the conditions have been. And hopefully this is actually illustrating that this is not a very simple problem. For a boat like this is scene 2. And well, there's somebody sailing there. It probably did not hit the boat. This is another scene, and you can't see that here on the screen, I suppose. You've seen the LED, it's coming again. Watch for it. But what you also may see is that it's raining. And it's actually pretty tough conditions for the boat as well. It's going up and down a lot. And scene 5 is one where we have a buoy there, and just illustrating that this is rather stable sailing and, well, probably a more benign scenario in a way. But what you've also seen is the buoy is going out and coming in again. So what we evaluate is how stable it is. And when we get the buoy back again, it takes a while till we actually see that this is a stable object. So for a while we assume, oh, it's new, it's completely new, we don't have a history of that object, and that you will see in my evaluation now. So looking at the horizon, you, well, Paul can't, see down here what the number of frames are, the number of frames where we actually get lines, good lines, and the number of correct detections of the horizon. And all in all, what you see is this one is not all that great, and if you look here, well, tell me where's the horizon? Can you see that? Can't be met at the algorithm. And here, well, this is where we have the rain, and sometimes we have actually raindrops on the camera or some lines in there, and that also somehow made this a more tricky scene, apparently. Just briefly, these are different other scenes, and down here you just see how many lines or horizons have been detected correctly. I want to point out something here. So quite often we do have the problem that we have a second line below the horizon, which is really, really close by. It did not count as a correct horizon for us. But for all purposes where we need the horizon, for instance, to estimate the heeling of the boat, it would still be the same information. And same here. So in this case, we also have this problem that there is a second line very close by. And again, you see that most of them are fairly good, like well above 80%, except the 2 for these 2 down here. For the buoys, well, same idea. We had different scenarios, and these are again the same scenarios as before. And you see down here how often could we identify a candidate if it was visible, and in quite a few cases we found it really, really often. How often did we find it stable? Well, there you see that sometimes the buoy was missing in the image completely, so then it was not stable, so this number is much lower indeed. But that doesn't mean that the algorithm would work. And if you look up here, this one, well, there is a yellow buoy there, but I can hardly see it. And this was a problem apparently for the algorithm. And this is a scene where we identify the buoys, and you see also there is some shaking going on. And the buoy is leaving and leaving again, and so it's not all that easy. And some more results from Tobias' thesis, also indicating there's a buoy that we don't see very well, and well, you see down here there are complicated situations sometimes. The last thing, well, I don't even have a title on that one, is the comparison of actual compass and the optical flow, all in German here, but anyway, so what you see is that the optical flow agrees fairly nice to the compass readings, except that you don't see those spikes. Now, I don't know whether the compass is right with the spikes or whether the optical flow is right with not having the spikes in this case. And actually, we hope that potentially the flow could give us a smoother estimation of changes in the rotation, particularly changes, not the actual compass reading, of course, but changes in the orientation than the compass may do. The compass is actually very much affected by healing, so there is a reason why we could see spikes there. Just to give you some idea of the limitations of all that, well, lighting, of course, is always a big issue if you have visual sensors, and over here you see there's lots of reflections and dazzle in here, and this is not a situation where you can use this approach readily. Luckily in Germany we don't have sun that often, so we are not affected by that. I believe, or hopefully, maybe, potentially, I can tell you what this is. So this is an approach to a line, and you see that, well, hopefully we could use some approach like this to make the line at some point without relying on the GPS data and hitting the buoy. So results are encouraging somehow. We could augment other sensors potentially. I believe that our evaluation was rather conservative in that we've been fairly picky in terms of identifying, for instance, the horizon, and it may be sufficient to detect it somewhat close to the actual horizon. However, it requires much faster onboard processing to actually get that in the boat. So now, here's the onboard processing. It's not good enough yet. I have to wait another 2 years until I get an eBay phone that is actually capable to run the algorithms online. Ours are at the moment at about 20 to 25 hertz on a real computer. But I just wanted to illustrate that I believe 2, 3, 4 years down the road we will get such devices that can do all this online. And this was before we started the conference from here. This was where you've been when I took this picture. This was what happened outside, and the only boat I could see was Beetle Bean. Thank you very much.
Thank you very much, Alexander. Are there any questions?
You mentioned that for locating the horizon, you base the measurement in similarity. How do you define it? Because you can imagine that the sailboat is moving. So in that scenario, how much similar is one line in a frame to another line in a following frame? Do you correct the images somehow?
No, at the moment we don't. We just assume that it is like the frame rate is much higher than the motion that we see in reality. So at the moment we have two components. We have the point and we have the slope. And we just compare the two. This is what's in the similarity measurement, or in this dissimilarity metric. And essentially, if I have very, very rapid motion, it won't work anymore. But actually, most of the time we get some estimate, and we hope to keep that. More questions?
There are so many questions, I'm not sure whether we can. That was Mark, then Jose.
So have you played with panoramic cameras at all?
I would like to. Do you have one?
Yeah. There's a really easy trick you can do with an ordinary camera. You just use either a big shiny ball bearing or a cone.
Well, think of bubble picks for iPhones now that does it.
Yeah.
Well, I couldn't get hold of anything that I could put on there, well, cheaply. And
what we do is you use a glass tube.
Yeah.
You cut the glass tube and then you just glue a nice shiny stainless ball bearing at the end of it and stick it over your lens. It actually works quite well. You get some internal reflection problem.
That's a very good idea.
But that's one funny. But there's a whole load of work being done by colleague Fred Laperosse and I have a PhD student looking at attitude estimation, and the algorithms they use are just really simple distance metrics between images. And computationally, they're a lot cheaper than things like optical flow and stuff like that. You don't have to do any identification of points. So I think your last slide, you're on the right track when you said, oh, we don't need to identify it perfectly. if you can do the stats, then the nice thing about doing it with all the pixels individually and not worrying about detecting lines and stuff is that you get sub-pixel resolution for all your estimates because you're averaging everything together. So you can actually get really good estimates of orientation, both in compass but also in attitude. And if you have a panoramic camera, it's even better because it all evens out front, behind, and
I believe Fred did that on the panoramic camera,
Yeah.
and so I absolutely agree. You could extend that. We've just used the OpenCV methods
Yeah.
because we had them readily available.
so
And
computationally it's a lot cheaper. That's the really nice thing about it.
yeah,
'Cause you just
well, it
subtract
would
the
be
pixels.
actually a good idea to compare different algorithms there and to see what could be implemented on a small device.
Yeah.
Absolutely. Yeah.
Good stuff though. Right.
Alex, one question about the computation times. That tens of milliseconds was per frame on the smartphone?
No,
On a
per
PC?
frame on a real computer
Okay.
with Fedora Linux and 4 gigabytes of RAM. So now it's not going to happen on the smartphone.
But do you have any estimate of computing time on the smartphone?
Not yet. Not yet. Probably much too long.
Yeah, sure.
But so at the moment, I believe probably you could maybe get 1 hertz or something like that. However, it is also kind of a function of the resolution. So on the smartphone at the moment, I do a preview with 320 by 240. This was 700 something by 480. I believe it may actually, there may be a trade-off. I can get down with the resolution because, for instance, this motion stuff doesn't really depend on a high resolution. You get a lot of information anyway. It may actually get better because you may have better features in the images at some point. So, but that is something. This phone is, well, I own it for 4 weeks. I also own a Yo-Yo for 4 weeks, and I do not own but have a summer intern who was playing with that guy. I don't have results on that. If I can get anybody, somebody working on it, I would love to compare it and get it run. And actually now we have quad-core phones, which is also an issue if you can actually parallelize some of that work, like having the, I don't know, the filtering everything, like image processing, maybe even get a better GPU on the phone at some point. But I can't give you numbers at the moment.
Maybe one very last short question.
Roland, I did not finish yet. Alex, another question. Did you try the horizon detection with low contrast horizon, for example, at OpenSea?
No, no. So our when we defined the scenario, it was clearly inshore and for this racing zone.
Green, blue?
No, no colors.
Okay.
It's just edges, just edges. So if you have a good contrast out there, it's all fine. If you have haze out there on a real ocean, well, it won't work. If there's no edge, there's no horizon.
Okay, Jose.
Yeah.
Says a lot about the quality of your talk, and so many people are interested in it. But I would ask to have one very last short question, and then we can use the coffee break for further
Most
discussion.
definitely.
I was just wondering what was the distance metric you used in half transform? Was it just a straightforward Euclidean distance?
For the half transform?
Yeah. Between the
No, between the lines, you mean?
Yeah, yeah.
Well, it was not really straightforward. It was weighted.
Okay.
It was weighted from point, or one part was a point, the difference at point, and the other was the difference in slope. And the two were weighted.
Okay.
Okay, thank you.
Okay.